You guessed it, there's also a law of sines. Maybe less complicated to look at, but no less useful. I'm actually starting out with a proof of it. You don't need to remember how to do this, but it's actually quite simple, and I think it helps to motivate the law itself. If you just look at a random triangle up here on the top with angles ABC and sides ABC, and if I draw a line down from C to the side C, from angle C to side C that is perpendicular to the base AB, you will notice that the sine of angle B is that altitude h divided by a, because I have a right triangle there now on the left side. But I also have a right triangle on the right side, and I can use that to show that the sine of angle A is h over b. Rearranging these and setting them equal, because h is equal to h, we find that a sine b equals b sine a. Rearranging this yet again, we get the law of sines. A over sine a equals b over sine b. We could do this again, drawing an altitude from a different angle to a different side, and we would also find that these two ratios are also equal to c over sine c. And that's the law of sines. And this law is very useful when you have two angles and a side, and that side can either be the side between the two angles or not. Those we call AAS and ASA cases. ASA. It's also useful in a case called SSA, which I've written in red because it's special and difficult. I easily remember which one is the difficult, nasty one by just looking at the word SSA and thinking about how it might sound if you spelled it in exactly the reverse order. I'm not going to pronounce it, but you know what I mean. It's easy to remember the nasty one. Okay? All right. Well, example 1 in your text shows how given two angles, you can easily find the third using the fact that the angles must sum to 180 degrees, and from there using the law of sines to find out all the remaining unknowns in the triangle. All right, so from now on in this section's explanation, I'm going to focus on the SSA case because that's really the hard part. And the nastiness really comes from the fact that when you do the inverse sine of something, you can get two answers, one answer, or no answers, depending on the situation. With the SSA triangle, the first case is that side A is less than side B, and as you'll be able to see in a moment, that there is no triangle that works, that there's no solution at all. The idea is that we're given the lengths of two sides, side A and side B. In this case, A is 3 and B is 5. If you look at my little diagram here, A is the little red side and B is labeled as 5. And angle A is 40 degrees. You'll see that side A just doesn't reach down to make a triangle. It just doesn't reach. It's just not long enough. You can imagine swinging it about a hinge that would be in the position where angle C would be. And no matter where you swing it along that dotted line, you can't make the three sides connect. You can't make a triangle. So in a situation like this, there is no solution. Now, how is that going to look algebraically? Okay, so if we try using the law of sines, b over sine b equals a over sine a. That's 5 over sine b equals 3 over sine 40. Be careful that you're in degree mode here. Cross multiplying and dividing by 3, we find that the sine of b is supposed to be 1.071, and that is never going to have an answer because, as you remember, the range of sine is between -1 and 1. You can't have an angle whose sine is 1.071. It just doesn't exist. So there is no angle that makes this work. This triangle has no solution. And this will happen sometimes when you're given an SSA triangle to solve. So be on the lookout for this kind of thing. Case 2 for the SSA triangle is again that A is less than B, but B happens to be a 90-degree angle. Okay, and I've drawn an example of that here. To make that work, we can have A equal to 3.214 and B equal to 5, angle A 40 degrees. When we try setting up our law of sines to solve for angle B, we cross multiply and divide by 3.214 to find that the sine of B is 1. Oh, well, that'll work. That'll work if B is 90. And to find the other possible answer when you do the inverse sine of 1, well, the other angle is always 180 minus the original answer. And 180 minus 90 gives you 90 again. So you get the answer is 90 or 90. So that's it. The answer is 90. B is a 90-degree angle, and there's only one triangle. So that's another case that's possible with the SSA triangle. Case 3 is the trickiest one. A is less than B again. In this case, we have two possible solutions. I've made A 4, B 5, and angle A 40 degrees. Look at this drawing for a minute. I can make two different triangles, ACB1 and ACB2. ACB1 has angle B1 as obtuse, bigger than 90 degrees. ACB2 has B2 as acute, less than 90 degrees. Watch how it works algebraically. Setting up A over sine A equals B over sine B, I end up that the sine of B has to be 0.803. Using inverse sine, I can find 53.5 degrees. But, as we all know, 180 degrees minus that is also a viable answer. One answer is acute and one is obtuse. Now I can follow each of those answers through to find angle C and side C. And that's exactly what you have to do in this SSA case. When they say solve the triangle, and it's one of these, you actually have to get two sets of answers. Alright, so far we've had no answer, one answer, and two answers. In case 4, we finally have A being either equal to or greater than B. In this case, 7. Right? Now you can see that I have the same kind of triangle I've had all along, but there's no way that I can swing this side, the red side, around and make a second triangle. You know, I can't push the side that's 7 units long over to the left because it's just not going to fit. And so when we solve this triangle algebraically, we end up sine of B is 0.459, so inverse sining that, we get 27.33 degrees. So we think, all right, well, what about 180 minus that? And we get an answer, 152.669. That looks right, but it doesn't work. Why doesn't it work? Well, if I try adding that to the 40 degrees that's already there in the triangle, I'm already over 180. So this answer is not a real answer. So don't be fooled into following it through. It's not a real answer. There's only one answer in this case. This section also has some handy formula for calculating the area of triangles, even if they're not right triangles. Okay, the first one is useful if we know two sides and the angle between them. It's just called the area formula. A equals 1/2 AB times the sine of the angle C. And the second one gets named after an ancient Greek guy named Heron, and it's called Heron's formula. And it uses a symbol called S. S is known as the semi-perimeter. It's the perimeter, A plus B plus C, times 1/2. Okay, and then it's ugly, root of S times S minus A times S minus B times S minus C. And here's a simple example of how that works. I think you can follow it through with no problem. It's easy to apply. You just have to calculate S and then plug it in and get all the bits and pieces right. Take the square root, in this case, 2.905. And here's an example of using the other area formula. Okay, here, as you can see, we have two sides that we know and the angle between. We just plug in to the formula 1/2, one side times the other times the sine of the angle between, and we get the answer 20.229. Alright, so once again, a bag of tricks, easy to use, just a bit complicated to look at. Please start making your cheat sheet now. You'll be able to have one for this test, of course. Alright, for homework in this section, I'd like you to work on page 634, 1 through 57 odd. It's a lot, I know. It's going to take you a while to do, but the practice is going to help you to understand these things better. Good luck.